All right, advanced placement chemistry class. There's 5 more days until the AP exam. This is Sunday, May the 10th. And what I wanted to do is go over Unit 6. I'm skipping over Unit 5 for a day, and then we'll get into that. So I'm going to go over Unit 6, which is thermochemistry. So what that is it's how heat relates to chemistry. Now, why is that important? Well, when you took physics, you learned there's all different kinds of energy. There's mechanical energy, that's motion. There's electrical energy, wave energy, sound energy, nuclear energy. There's a lot of different types of energy. But in chemistry, except when we're talking about quantum theory with atoms, chemistry always means heat. And so we're going to study how heat goes into and comes out of a chemical reaction. And by studying heat, we can learn about the general energy structure of chemical bonds, of chemical compounds, and of chemical reactions. All right, so I'm going to go ahead. These notes are about 15 pages, and I'll move through them. They're the same notes that you had in the class in the fall semester. So temperature, let's define that. Temperature is the average kinetic energy of atoms and molecules, and we're just going to refer to those as particles. Rather than having to say atoms or molecules, just refer to them as particles. In a solid, liquid, or a gas. Although the particles in a solid can't move around, they can have kinetic motion energy by vibrating in place. They can vibrate. In fact, there's nothing in the universe that's standing still. Everything is moving in some way. Heat. Heat is the transfer of energy between two objects of different temperatures. The kinetic energy in one object transfers heat energy to increase the kinetic energy in another object. So note that the object can be the air. That heat can be released into the air. So if there's a hot metal railing outside at school, it has a high degree of a high temperature, and the kinetic energy of those molecules is very high. They're wiggling around a whole lot. Since they're metal, they can't move, but they're wiggling a lot, back and forth a lot. Now, if you then touch that metal with your hand is cooler than the metal, so the heat will transfer out from the metal into your hand, and it'll burn you a little bit. So that's a transfer. So that energy transfer from the metal bar to your fingers is heat, whereas the internal energy of the molecules in the bar is temperature. Now, in the morning, early in the morning, when that bar is really cold, it has a much lower kinetic energy of its molecules. So if you then touch the bar, your hand will be warmer or hotter than the bar. It will have more kinetic energy, and so you'll have a heat transfer of energy from your fingers into the bar, and that gives you the sensation of coldness. So heat and temperature aren't the same thing. One is internal to an object or to a substance, and the other one is a transfer of energy into or out of that substance. The unit of measure for energy, heat, and work, and we'll talk about work in a minute, is a joule. So any kind of energy is measured in joules, and heat is measured in joules. For example, we want a car to do work moving us. To do this, the car must have stored energy called gasoline. So the gasoline would be the energy, and it would be stored as chemical energy, as potential energy in the form of chemical bonds in the gasoline. And then when you break those chemical bonds, you can release the energy into the car. And what will happen is two things will happen. Some of that energy will go into moving the car, and that will be called work. Work requires that something move, and then you study about that in physics. Work equals force times distance. It has to cause something to move. So some of the energy in the gasoline is converted into work, making the car move, but most of it is actually converted into wasted heat energy. So all of the energy, stored potential energy in the gasoline, either goes into work or heat. We'll get to that equation coming up here. Chemistry, the calorie is also used to measure energy, but we won't in this particular unit. Just a note that a calorie is 1/1000th of the energy of the calories on a food package. So if a food package says it's 100 calories with a capital C, that's really 100,000 calories that we use in chemistry. But again, we're not going to really use that in this unit at all. So thermodynamic analysis is usually divided into two spaces. The system. The system is what is being analyzed. It could be a single atom or a container of substances. For our purposes, the system is where the chemical reaction takes place. So it's not so much a place as it's an event. It's the chemical reaction. That's what we think of as the system. That can be taking place in one place or spread out over different places, but that's what we think of as the system. It's the object of our attention, is that chemical reaction. The surroundings is everything else that's outside of the system. It's the rest of the world, but really it's the immediate surroundings around the chemical reaction. So if you put the system and the surroundings together, that's everything. That's called the universe. Any energy that leaves the system must enter the surroundings, and any energy going into the system must have come from the surroundings. There's only two places in our simple world here. So this can be expressed as delta E, change in energy of the system, equals minus delta E of the surroundings. All it means is the numeric value of the energy going from system to surroundings or surroundings to system is going to be the same number. It's just in one case it's going to be a minus sign, in one case it's going to be a plus sign, and we'll talk about which is which in just a minute. The first law of thermodynamics states that energy is conserved, which means that energy is not created or destroyed. Energy can be converted from one form to another, such as heat, electricity, or mechanical. The relationship between energy, work, and heat is the following. So energy is defined as the capacity to do work. Energy can cause an object to move, work, abbreviated W, or produce heat, Q. So the example I gave of the car. The chemical energy from the gas either goes into moving the car or it's wasted as heat. The change in energy, delta E, is the sum of these two. Delta E equals heat plus work, and heat is abbreviated with the letter Q. Work with the letter W. So here's what's going on in chemistry. Let me get to this in a minute. Okay, so when work or heat is put into the system, the number is positive. So think of it like money into your bank account. When you put money into your bank account, that's positive. When you take money out of your bank account, that's negative. It's the same with heat or work in a chemical system or a chemical reaction. And we're more interested in heat, so let's focus on that in the diagram. If you put heat into a chemical reaction, then that's a positive, a number, and when heat comes out of the chemical reaction, that's a negative number. So when heat enters a chemical reaction, it is called endothermic. That's easy to remember. Just remember endothermic. It's going in. And when heat leaves a chemical reaction, it's called exothermic, like an exit sign above a door. It means that's where you go out. Okay, solids, liquids, gases. So these are the three states of matter. So solids, liquids, and gases are called states of matter. States of matter determine how atoms, molecules connect to one another. In a solid, atoms, molecules are in fixed positions, as the diagram shows. They're generally pretty rigid, and oftentimes they're very neatly lined up in rows and columns like you see there. Not always, but oftentimes. Liquid molecules are attracted to each other through intermolecular forces, but very loosely. So they stick together, but they can move around each other. And that's why you can slosh a glass of water around. So that's a liquid. And then gas molecules are completely detached from each other. As long as you keep the temperature high enough and the pressure low enough, they'll want to fly around and not get attached to each other. So they're attached from one another. Okay, enthalpy. Enthalpy is the amount of heat taken in or released by a chemical reaction under constant pressure. What does constant pressure mean? It means you're doing the reaction in open air. So you have the atmospheric pressure pushing down on the reactants, and that doesn't change. You don't change your chemical reaction doesn't change the pressure in the atmosphere. It is what it is. Typically it's 1 atmosphere at sea level. So it just means you're doing your chemical reaction in open air, not in a closed container where the pressure could get greater or less. In chemistry, we are interested in changes in enthalpy that take place during a chemical reaction. Change in enthalpy is represented by delta H. So H is the letter for enthalpy, and delta means change in. So delta H equals Q. So we said that energy, we're interested in studying the energy in chemical reactions. And that can be either work or heat. but we want to avoid work. That's more a subject for physics, and it complicates the study of energy because it deals with moving objects, as we said earlier. So you don't want to deal with work. So what you want to do is do a chemical reaction in a situation where it's not going to cause anything to move. Therefore, the only way the energy can be taken in or released is through heat. And we have a way of measuring heat indirectly by measuring temperature. So enthalpy, the formal definition of enthalpy, is not something you need to really understand other than for our purposes, it simply means heat. Delta H, change in enthalpy, is heat going into or coming out of a chemical reaction. Heat going into a chemical reaction is positive, endothermic, and heat leaving the reaction is negative, exothermic. There are several kinds of enthalpies we're going to talk about. Sometimes they can get kind of confused, so let's just define a few of them right here. Enthalpy of fusion is the enthalpy associated with a phase change between liquid and solid. So ice melting is going to take in a certain amount of energy to make an ice cube totally melt into water. That's called the enthalpy of fusion. And if you want to freeze the water back into ice, you have to remove that exact same amount of energy to get the water to go back into the ice, to turn the water back into the ice cube. So that's energy coming out. Those are called the enthalpy of fusion. It's the heat that's put in or taken out when you're either melting a solid or freezing a liquid. Enthalpy of vaporization, that's the enthalpy associated with a phase change between a liquid and a gas. So such as water to steam. So when you boil water, it turns into steam, and the amount of enthalpy it takes to totally boil water, a certain amount of water into steam, is the enthalpy of vaporization. If you condense the steam back down into water, that's also the enthalpy of vaporization. When you boil the water and turn into steam, the heat is going into the water, so that's endothermic. When you condense steam back down into water, you're letting off energy. You're bringing the water down to a lower energy state. That's releasing energy out into the surroundings. And that's also enthalpy of vaporization. It's just the opposite sign. It's opposite direction. Okay, enthalpy of reaction is the enthalpy produced by a specific chemical reaction. The molar enthalpy of reaction, by the way, would be the enthalpy produced by reacting 1 mole of a substance. And oftentimes that's what you want to know. Enthalpy of formation is the enthalpy required to produce 1 mole of a compound from its elements in their most stable form and at standard state conditions, which is generally 1 atmosphere and 25 degrees. You'll see an example of this later, so don't worry too much about that. Okay, the letters after each product and reactant reflect the state of matter. There are 4 possible values that can be displayed. You've seen these before: solid, liquid, gas, and aqueous means something mixed in with water. Just think as your common example of salt water. That's an aqueous solution. It looks like a liquid because it looks like it's mostly water, so you'd say that's a liquid, but it's not. It's called a solution. If it's pure water, it's called a liquid. If it's salt mixed in water, even just a little bit, it's called a solution. The state, liquid, gas, or solid of products and reactants affect the enthalpy values of reaction. There's 2 terms that are used in chemistry. They won't explicitly ask you this on the AP, but you should know them. An extensive property is a property that depends on the amount of matter being used. An example would be mass or volume. So the more of a certain substance you have, the greater will be its mass and its volume. That's an extensive property. It depends on how much matter you're using. An intensive property is a property that is independent of the amount of matter. An example would be density. So iron, whether you have 1 gram of iron or a kilogram of iron, it still has the same density. That's the same amount of mass per unit volume. So it doesn't matter how much or how little you have, the density of iron stays the same. The rules of enthalpy. So enthalpy depends on the amount of reactants and products, making it an extensive property. In other words, if you burn 1,000 grams of methane gas, you're going to get a lot more heat, a lot more enthalpy coming out than if you only burned 1 gram. So the amount of matter does make a difference. The enthalpy of a reaction is the same as the enthalpy of a reverse reaction, but with the opposite sign. Okay? So coming out of this reaction would be a negative sign, like money out of your bank account, heat going in, enthalpy going in. You really say change of enthalpy, not enthalpy going in. You say heat going in would be a positive number. That would be endothermic. That would be positive. Enthalpy depends on state, liquid, gas, or solid of the reactants or products. So in other words, to turn liquid water into into steam, would require 88 kilojoules per mole of heat. So that it depends on what state you want the water in. If you want it in liquid or if you want it in steam, it's a different amount of enthalpy, a different amount of energy. Okay, specific heat capacity or specific heat. So specific heat capacity and specific heat mean the same thing. Specific heat tells how much the temperature of a substance will change when a certain amount of heat is put into or taken out of the substance. So different substances have different specific heats. Specific heat capacity is defined as the amount of heat required to raise 1 gram of a substance by 1 degree Kelvin or centigrade. A degree on the Kelvin centigrade scale are the same thing. So weighs 1 gram by 1 degree. That's specific heat capacity or specific heat. Heat capacity, so in other words, without the word specific on it, is the specific heat of a substance multiplied by the mass of a substance. So clearly, to raise water, to raise a kilogram or let's say a liter of water 1 degree centigrade takes more heat than to raise a milliliter of water by 1 degree centigrade. The more water you have, the more heat you have to put in to raise it by 1 degree centigrade. So that's heat capacity. Heat capacity is extensive. It depends on the amount of mass. Specific heat is intensive. It doesn't depend on the amount of mass. It's fixed for any particular substance. So specific heat capacity applies to 1 gram of a substance. Heat capacity applies to the entire mass of the object being measured. Okay, coming up here is the one and only really important equation in thermochemistry. It's the relationship between heat and temperature. We really don't have in chemistry a way to measure heat directly. When heat is coming out of a chemical reaction, we don't have a way to measure that. But you're all familiar with a thing called a thermometer. And a thermometer can measure temperature. So because of this formula, we're able to convert a change in temperature into how much heat. Remember, change in temperature is just molecules wiggling around, kinetic energy, whereas heat is the actual energy transfer or the energy that's stored in chemical bonds. So the formula is Q equals mc delta T. So what it means is the relation between a change in temperature and the amount of heat that's going into or coming out of a chemical reaction depends on C, the specific heat of the substance. So the specific heat, C, is a function of the substance. It's different for water than it is for say, iron. And then it also depends on the mass. Okay, the more mass you have, the more heat it will take to cause a certain temperature change. So there, Q is the heat, M is the mass, C is the specific heat. And we measure it in joule, grams per degree, either Kelvin or centigrade. Again, as long as I would always put things in Kelvin, okay? If in doubt whether it matters whether you use Kelvin or centigrade, it has to do with when you're talking about a change in temperature, the change on the Kelvin scale is the same as the change on the centigrade scale. So if you go from 0 to 100 on the centigrade scale, that's the same as going from 273 to 373 on the Kelvin scale. The numbers are different, but the difference between the numbers is 100 degrees in both cases. Anyway, to just, make the point, just convert to Kelvin if you're not sure. And then delta T is the change in temperature. The equation can be written in terms of temperature, delta T, so all you did is rearrange the equation. Sometimes you want to know the delta T for a given amount of heat. Okay, if delta T is negative, then Q is negative and the reaction is exothermic. That means heat is going out of the reaction. If delta T is positive, then the reaction is endothermic. Heat is going in. Okay, so example. So example of heat capacity being different is, think of touching a cup of water sitting next to an iron bar on a normal morning. The cup of water will be cool and the iron bar will be cold, like the railing outside in the quad somewhere at Hoover. Now, at 1 p.m., you touch the same cup of water and the same iron bar. The water's going to be a little bit warmer, but it's not going to be hot. However, the iron bar will be very hot. You might not even be able to touch it. So what does that mean? It means the same amount of heat energy coming from the sun caused very little change in temperature in the water, but it caused a big change in temperature in the iron bar. Generally speaking, the higher the specific heat, the less the change in temperature due to a certain amount of heat. In other words, water has a relatively high specific heat, so a certain amount of heat won't cause its temperature to change very much. Iron has a low specific heat, and so the same amount of heat put into an iron bar will cause its temperature to change quite a bit. So here I give the example right here using some numbers. So we use the equation to figure out the change in temperature. So the first equation, if you put 10 joules into iron, into 1 gram of iron, and you see the specific heat of iron there is 0.45, that's the C value, that'll be a change in temperature of 22 degrees. That's a pretty significant change in temperature. If you do put the same amount of heat, 10 joules, into water, you notice water specific heat is much higher, 4.18. So that'll be a temperature change of only a little over 2 degrees. That's not much change at all. You'll hardly even feel that. Okay? So higher specific heat means less of a temperature change for a given amount of heat being put in. So the same amount of heat added causes the temperature of the iron to rise almost 10 times as much as water, which explains why the temperature extremes in iron are much greater. Substances with low specific heat values will experience greater temperature changes when the heat is added or removed, what I just said. Also, small changes in temperature of these substances will take in or release large amounts of energy. Specific heat is an intensive property because it does not depend on the mass of the substance. Let me just take that word out there. So, in other words, with that formula above, you had to take the specific heat and multiply it by the mass in order to figure out exactly how much heat was going to go in or come out. Okay, here's kind of the serious part of this unit. In this unit, we will study 4 ways of measuring the energy absorbed or released by a chemical reaction. Calorimetry. There's 2 types of calorimetry, but they're both fundamentally the same. There's just differences in the details of how you do them. And one is called constant pressure, or more colloquially, it's called coffee cup calorimetry. Constant volume is called bomb calorimetry because you're literally detonating a combustible substance inside a closed chamber. Then we have Hess's law, enthalpy of formation, and average bond energies. Okay, none of these are that hard, but you should practice them. They're not going to ask you a lot of number questions on this test, but they could ask you bits and pieces of number questions in these. So you should, or they might just ask you conceptually to explain these. Okay, so let's start with calorimetry. Enthalpy is most often found experimentally by a process called calorimetry. That's really the only one of the 4 that we could actually do experimentally in a high school chemistry class. And you will be asked about this on the AP exam. Who knows about this exam, but there's a good chance. There's a good chance. This is one of the kind of processes or lab techniques or processes or experiments they'd like to ask about. Simply, calorimetry is performed by carrying out a chemical reaction in a container, the system, okay, and measuring the change in temperature in the surroundings. Okay, now the chemical reaction doesn't have to be in a container. It could be what we did in class is we threw sodium hydroxide into water. And so the system was really the chemical itself, and the chemical reaction itself. It doesn't have to be in a separate container. In theory, all of the stored energy in the substance will be converted to heat energy, which can be measured by the thermometer. So the only kind of energy that a chemical reaction gives off is heat energy. Since it's constant pressure, that means there's no work done. And so you eliminate work from the delta E equals Q plus W equals heat plus work equation. So that means your change in energy is only heat. So you're able to measure the energy in that chemical reaction because there's no work involved, only heat. Whatever heat is put out by the system, that's the chemical reaction, was taken in by the surroundings because that's the only place it can go. And we assume you have an insulated cup so it can't escape the surroundings out into the open atmosphere. Similarly, whatever heat went into the system, if it's an endothermic reaction, came from the surroundings. So just like we did with delta E, the Q of the system, the heat of the system, is the opposite of the heat of the reaction. So that negative sign could have been put on the other side. It could have said negative Q system equals positive Q surroundings. All it means is whatever heat came out of the system, that same exact number went into the surroundings. Out of means a minus sign, into means a positive plus sign. If the heat came out of the surroundings and into the system, it's going to be the exact same numeric value. It's just equal and opposite. Just think of it this way. If our classroom is the system and outside of our classroom is the surroundings, if I take 2 books from the classroom and place them outside the door, then the system, our classroom, has negative 2 books and the surroundings have positive 2 books. That's all they're saying. If I then take those books and move them back into the classroom, the surroundings has negative 2 books and the system has positive 2 books. Overall, the universe, it didn't change. Number of books in the universe, the two together, didn't change. But it's just saying that it's an equal and opposite number. Okay, constant pressure calorimetry, coffee cup calorimetry. So this means it's not doing any work. It means any energy coming out is not pushing on something, creating pressure. And if it's not pushing on something or making something move, it's not doing work. So it's all heat. All of the energy coming out is heat. It's the simplest because the container is exposed to open air, which provides a constant pressure. This type of calorimetry is often used for liquid solutions and simple, safe, non-volatile substances. In a coffee cup calorimetry, the thermometer is inserted directly into the solution, which think is sodium hydroxide mixed in water, a solution of sodium hydroxide in water. Sodium hydroxide releases heat energy. A stirring rod is inserted to mix the solution as the measurement takes place. Example of coffee cup calorimetry. Dissolving 6 grams of calcium chloride in 300 milliliters of water causes the temperature of the solution to increase by 3.43 degrees centigrade, which could also be 3.43 degrees Kelvin. Assuming the specific heat of the solution is 4.18, so if you have a solution with water, you just use the specific heat of water because the vast majority of the solution is water. So that's the specific heat of water, and so we're using that for the solution. And assuming the calorimeter absorbs no significant amount of heat, in other words, no heat goes into the cup, the styrofoam cup that you're using, determine the delta H, that's the enthalpy, for the reaction. So if we look down below, there's the chemical reaction. So most problems will assume that no heat is lost in the calorimeter itself or into the atmosphere, into the open air. If you do the experiment quick enough, very little heat will escape into the open air. Now define the system and the surroundings. The system in this case is not so much a place, it's the reaction. It's taking place all over the solution, all around the solution. So wherever bonds are being broken from that calcium chloride, that's the system. So the chemical reaction, rather than being a place, it's an event. It's the chemical reaction. So that's the ionic bonds and the calcium chloride being broken. The surroundings is the water plus the calcium chloride. So the mass of the surroundings is the 300 grams of water plus the 6 grams of calcium chloride. So that's going to be the mass that's absorbing the heat, is both of those together. So there's the equation, the only equation you need. So it's MC delta T. And since the temperature is going up, it means the heat is coming out of the reaction and into the water. So the Q is positive for the water and negative for the reaction, and we're really interested in the reaction. So the mass is 306, the specific heat of water or of the solution is 4.18, and the delta T, the temperature change, is 3.43. So what you then get is negative 4,391 or negative 4.39 kilojoules. Usually express your answers in kilojoules with this when dealing with enthalpies. Okay, the heat of the reaction is the heat released by the reaction as shown, which is 1 mole of calcium chloride. So you figured out how much heat was released by 6 grams of calcium chloride. Okay, the only thing releasing the heat is the calcium chloride, not the water. That's just catching the heat. So the heat of reaction, delta H of reaction, is the heat released by the reaction as shown, which is 1 mole of calcium chloride. So you use a grams to mole conversion to figure out how many moles is 6 grams of calcium chloride. So that's done below, and it's 111 grams of calcium chloride for every mole. So, and you were using 6 grams of calcium chloride, so that'll tell you how many moles you have. And then you just divide the 4.39 kilojoules by the number of moles that you actually used, however many moles 6 grams of calcium chloride is, and that'll tell you the energy per mole that's being released by breaking the bonds of calcium chloride, by breaking all those ionic bonds. That'll tell you how much heat came out and therefore how much energy is coming out of the calcium chloride, and that happens to be negative 81.1 kilojoules per mole. Okay, constant volume calorimetry. This is called bomb calorimetry. It has a constant volume, means you have to have a lid on it because you're going to actually literally explode something, make something explode or burn something. And it's performed in a sealed container where the volume cannot change, but the pressure can change greatly. So if a bomb goes off, it's going to cause a great change in pressure. This type of calorimetry is used for explosive or volatile substances, such as gasoline, and requires an igniter and a more complex device. So you literally, instead of throwing the sodium hydroxide in the solution like we did in the last one, this one you actually have it in an enclosed container. But the heat is able to escape from that enclosed container and get out into the water in the same way that it did in the last one. In the last example. A bomb calorimeter contains a closed container with the substance sealed inside. This container is submerged in water within a larger container. The substance is ignited by a spark and burns, combusts, possibly explodes very quickly. The thermometer is in the water, just like it was in the last example, and, of the larger container, and displays the amount of heat released by the combustion. Okay, so in this next page, what I've given you is a bullet point explanation of calorimetry, either type, just so you understand the concept. Be sure you can explain this clearly, because there's not a bad chance you could be asked something about it on the test. So here's a simple bullet point summary of calorimetry that you should be able to express on the AP exam using the substance methane as an example, CH4. And methane is going to produce an exothermic reaction. It burns, it's like a gas, so you're burning it in a bomb calorimeter inside of a chamber, although this explanation applies to either type of calorimetry. Okay, so number one, the heat is released or gained, but in this case it's released in a chemical reaction of a known mass of methane. Now, we don't have a way to measure heat directly. There's no thing called a heatometer that we can measure heat. So heat cannot be measured directly. The heat is released into an insulated cup or a container, so it can't escape. The heat still can't be directly measured, but it causes the kinetic energy or motion energy of the water molecules to increase, which causes the temperature at the thermometer to increase. So the heat goes outside of that chamber. The amount of heat leaving that chamber is the same amount of heat that's going into the water. The heat's not just going to one location. One thing about water is it'll take the heat and spread it out all around the water evenly. But it's the same amount going out. So that's a negative Q for the system, for the methane. The heat is going out. And it's a positive Q for the surroundings, which is the blue part, which is the water. The heat is going in there. And it's the same numeric value. It's just an opposite sign. Okay, but even though we have heat out of the water, we don't have a way to measure heat. But we do have a way to measure the temperature of the water, and that's the thermometer up on the top. So number 4, using the formula Q equals MC delta T to relate the temperature increase to the amount of heat. We use that. So C is the specific heat of a particular substance. In this case, we're interested in the specific heat of water. The mass of the water also matters. The more water, the less temperature, the temperature will rise from that particular amount of heat. So we need to know the specific heat of the substance, which in this case is water. We need to know how much water we have. That's the M and the C. And then the change in temperature, that's the delta T. So the equation relates the temperature on the thermometer to the amount of heat released in the water. Number 5. The heat into the water is the only energy released by the methane chemical reaction. This is very important. There's no other energy being released by this methane. It's in a constant volume. It can't do any work because it can't make something move. Work requires that something actually physically move. It can't make anything move. And there's no other type of energy. There's no light energy or sound energy or anything else. So it's all 100% heat energy. So that's number 5. Number 6, the heat entering the water came entirely from the methane. So there's no other heat in that water. Well, once we take the initial temperature, we know there's no other heat that was put into that water. And so here's the conclusion, and this is almost everything put together. All the energy stored in the chemical bonds of the methane was released in the combustion as heat when you burn the methane. Entered the water, caused the temperature of the water to increase, and finally could be quantified, put into number form, using the equation Q equals mc delta T. So that's what relates something we can measure, which is a change in temperature, with something we can't measure, which is heat. By knowing the mass of the methane, we can calculate the number of moles. If you know the mass and you know the molar, the substance, then you can do molar mass to figure out the moles. This allows us to know how much energy is in the bonds of a mole, or even a molecule, if you want to do the calculation, of methane. So that's all there is to calorimetry. So be able to give that explanation by Thursday on the test. So here's an example of constant volume bomb calorimetry, and there's CH6N2. It's a rocket fuel, so it's clearly an exothermic reaction. It's going to put out heat, and there's the reaction. So when 4 grams of methyl hydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 centigrade to 39.5 centigrade. You don't have to convert to Kelvin, but if you're not comfortable about the explanation why, go ahead and do it. The heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree centigrade. Calculate the heat of reaction for the combustion of 1 mole. So here's how a bomb calorimeter differs from a coffee cup calorimeter. You don't get the specific heat of just the water. You take the specific heat of the calorimeter, which is the water and the actual device itself. Why you do that, you don't need to really understand the details of that. It's just the way you would explain it properly in bomb calorimetry. So let me say it again. With coffee cup calorimetry, that's constant pressure. You just wanted to know the heat capacity of the water, which is 4.18. But with bomb calorimetry, you need to know the heat capacity of the calorimeter system, which is the water, the calorimeter setup, which is the water and the actual object, the actual device that's the actual container that's holding the water. And you have to measure that separately in a separate experiment. So that's what makes bomb calorimetry a little bit different. But I wouldn't get too lost in that detail. So assuming that you know it tells you that the heat capacity of the calorimeter is 7.794 and the delta T, so you don't need to know mass of in other words, of the water or the calorimeter. You don't need to know specific heat because you've already figured out the heat capacity of the calorimeter. So it's simply two numbers, 7.794, the heat capacity of the calorimeter, times the change in temperature, and that gives you the Q of the reaction, and that should be a small q, the heat of the reaction, and that's negative 113 kilojoules. So you figured out, so it's 113 kilojoules was produced by 4 grams. So now you figure out how many moles is 4 grams of methyl hydrazine, and it turns out to be 0.087 moles. So if you want to know the kilojoules per mole, that is how much heat is produced per mole, which is often what you want because it's a standard amount, then you just divide the negative 113 by 0.087. That gives you negative 1,300 kilojoules per mole is the enthalpy or energy that's being released from 1 mole of that substance. Okay, let's go into thermochemical equations, chemical equations involving enthalpy. So we have performed calculations on chemical equations using grams and moles. Now we add kilojoules. So you can think of heat as almost like it's a reactant or a product of a reaction. You have your reactants on the left, you have the products on the right. If it's exothermic, then you have heat coming out, and you think of that as a product, heat going out. If it's an endothermic reaction, it means that heat has to be taken into the reaction in order to make the reaction take place. So that would be like a reactant. It would be something you have to put into the reaction to make the reaction take place. And so the way you simply do it is you write the chemical reaction the way you always have, and then at the end of it you write delta H equals, and it's either negative number, which means it's exothermic, the heat is going out, or it's a positive number, it's endothermic, means the heat is going in. This means that 6.1 kilojoules of heat must be absorbed by ice to melt 1 mole of liquid water. So that's what this is saying, to take water from solid into liquid form, that is to melt ice. It takes 6.01 kilojoules. This means it's and that should be per mole. So let me add that here. So it's got to be per an amount of water. Clearly, more water is going to require more heat to melt the ice, and less water is going to require less heat to melt the ice. Okay, let me read this again then. This means that 6.01 kilojoules of heat must be absorbed by the ice to melt 1 mole into liquid water. So here are a few rules. Reversing the reaction changes the sign on the enthalpy, okay? So if you turn this reaction around and went from liquid to solid, it would be the same amount of heat per mole, but it would be a negative sign. It means you'd have to take that heat out of the water in order to get the water molecules to freeze together into a solid. Multiplying the equation multiplies the enthalpy. So instead of doing 1 mole, you want to do 2 moles. Then you just multiply everything by 2, including the enthalpy. Okay, and the third one in that table there is always state the state. Okay, you got to tell whether it's a solid, liquid, or a gas, or aqueous in a thermochemical equation, because the only change might be the change of state, like the example up above with liquid water and solid water. The only change was a change of state. So here's an example. Take the balanced equation. There's a balanced equation for the combustion of methane gas, and for every mole you get 890 kilojoules. So this equation, you get 890 kilojoules. Now it's per mole because you have 1 mole of methane gas. If there had been more than 1 mole of methane gas there, like 2 moles, it would have been the amount for 2 moles of methane gas. So this equation is read: 1 mole of carbon dioxide and 2 moles of water can be produced from 1 mole of methane and 2 moles of oxygen by an exothermic reaction releasing 890 kilojoules of heat. So that's how you would read that reaction. Okay, so what will be the enthalpy if 2.5 moles of oxygen is reacted in excess methane? This means that the methane is not the limiting reactant. Okay, you have enough. So you know that 2 moles of oxygen will produce, so we look at the equation. So we see 2 moles of oxygen in this equation will produce an enthalpy of negative 890 kilojoules. So if you use a half a mole more, so instead of 2 you use 2.5, then you would simply increase the amount of enthalpy. So let's just look at the calculation here. So you get 890 kilojoules for every 2 moles. You see that in the center of the equation there. And that's going to tell you how many kilojoules per mole. If you then multiply that by 2.5 moles, that'll tell you how many kilojoules you'll get from combusting 2.5 moles of oxygen. And that's negative 1,112.5 kilojoules. Okay. How many kilojoules of heat can be obtained from 25.4 grams of CH4 in excess oxygen? So you have all the oxygen you need. Well, remember, chemical equations don't know about grams, they know about moles, so you do a molar mass conversion. So 25.4 grams times 1 mole over, we'll just round it to 16 grams for CH4, that's the molar mass of methane. And then you know that you have negative 890 kilojoules for every 1 mole. So if you cancel all the units, you end up with 1,412 kilojoules. And that should be a negative because it's exothermic. Okay, let's keep going. Energy diagrams. You should know how to look at one of these. They're very simple, but you should know what they mean and know how to interpret them. Energy diagrams for a chemical reaction are shown below. The diagram on the left shows the energy of the reactants before the reaction. That's over on the left-hand side. So that's where the energy is. It's where it says energy of reactants. The higher amount of energy is called the activation energy. So the top of that mountain is called the activation energy. That's how much energy you have to put in to get the chemical reaction to start. So a simple example is, again, think of methane gas. If you just put methane gas together with oxygen, which is what the chemical formula says, it's not going to start to burn. You have to light a match. You have to give it an kind of a push with the energy, and that's what the match does, and that's called the activation energy. And that's the energy required to get a chemical reaction started. Once you light methane gas and oxygen, you get that match going. You can pull the match away and you can put the match out, and the burner in the lab will keep burning because it produces its own activation energy for the rest of the reaction. So once the reaction has started, the energy of the products. Let me move this thing. This is skewed a little bit. Okay, there we go. That's better. Okay. Once the reaction has started, the energy of the products can be higher than the reactants. That's the left diagram, which is an endothermic reaction. So think about it. You start at the energy of the reactants. The energy of the products is higher. That means energy went into the reaction. So that's an endothermic reaction. Or it could be lower, such as the diagram on the right. So you started with a certain energy of the reactants. You ended up with less energy in the products. That means energy came out of the reaction. That's an exothermic reaction. All right, enthalpy of formation. Enthalpy of formation is the enthalpy required to create a single chemical compound such as H2O. So the standard enthalpy of formation is the change in enthalpy for a reaction that forms 1 mole of a compound. So that's a key, that's why it's underlined, from its elements, with all the elements in standard states and in their most stable form. And this is denoted as delta HF for the formation, and the little circle means standard. So it means at standard state conditions, 25 degrees, 1 atmosphere. This is known as the direct method for finding the change in enthalpy of reaction, delta H of reaction. The fraction coefficient, notice you have something you almost never see, is a fraction coefficient. And that's there because the fraction as a coefficient is because standard enthalpy of formation requires that exactly 1 mole of water be produced. So if you have 1 mole of water, you got to have half as many moles of oxygen. So that means you have to have a 1/2 in front of the O2. So it's about the only place you'll ever see a fraction for a coefficient. Okay, so here's an example. To form 1 mole of magnesium carbonate from its elements in their most stable form looks like this. You have magnesium as a solid. Okay, you have magnesium as a solid. You have carbon in graphite form. You may remember we talked about that. Diamonds are also 100% carbon, but they are not as stable as graphite, surprisingly, even though they're really hard. So carbon and graphite is the most stable form. Graphite is the most stable form of carbon. And then 3/2 oxygen, and oxygen in its most stable form is a gas. And that will give you MgCO3, and that produces a delta H of formation of negative 1,112.9 kilojoules per mole. So what is the delta H of formation for O2? Since the most stable form of oxygen, O2, is oxygen O2, the reaction would be O2 gas to O2 gas, so the delta H of formation is 0 kilojoules per mole. The delta H of formation, this is important, of any element in its most stable form is always going to be 0. So H2 would be 0, N2 would be 0, magnesium solid would be 0. Any element in its most stable form is going to be 0. Enthalpies of formation are measured when the reaction takes place in the standard state. The standard state is defined as 25 degrees centigrade. That's technically not true, but it is for our purposes. It can actually be other temperatures, but we're going to say it's 25 degrees and 1 atmosphere of pressure. It's definitely 1 atmosphere of pressure. We will discuss these measures in detail later, but they are about the conditions of temperature and pressure. They're the conditions of temperature and pressure you feel, in the classroom or at any particular time, like right now. Enthalpies of formation for pure elements in their standard states is defined as 0. We just said that for oxygen. For example, O2 is the standard state of oxygen, so even though there are 2 oxygen atoms bonded together, this is the standard state for oxygen. So enthalpy of formation for O2 is 0. Standard enthalpy change of a reaction is the enthalpy when all of the reactants and products are in their standard states. Here are a few examples of standard states, solid, liquid, gas. So H2 is in its standard state, is in its most natural form as a gas. Same with oxygen. Water is considered to be in its most stable form as a liquid. Carbon as solid graphite. Magnesium as solid metal. H and O in their element form are molecules H2 and O2, that as a gas. Carbon is a complex molecule that can take many forms, including buckyballs and diamonds. Carbon in graphite form is considered to be its standard state configuration. Standard delta is the change in enthalpy that results from a chemical reaction. It is given by the formula. Okay, standard delta H of reaction, I should say. Of reaction. Okay, standard delta H of reaction, and it should have a little circle up there too. And so there's the formula. So you take the sum of the delta H of formation of the products times the number of moles of each of those products you have, and you subtract from that the sum of the delta H of formation of the reactants times the moles of each of those reactants you have. That's all it is. Formula looks ugly, but when you see it done, it's simple. Okay, so this equation means that you take the enthalpy of formation of each of the products times the number of moles of each and subtract the enthalpy of formation of each of the reactants times the number of moles of each. So compute the enthalpy of reaction of the following equation using the following enthalpies of formation. So if they asked you this, they would give you these. So C2H2 is 226.6 kilojoules per mole. That means you have to put that much energy in to get that to form. CO2 is a negative 393.5. That means energy comes out when you put carbon dioxide together. And H2O is negative 285.8. That means when you put 2 hydrogen and oxygen together to form liquid water, 285.8 kilojoules per mole comes out of the reaction. So there's the reaction there. There's the balanced reaction. And so each of those numbers you saw up above for CO2, now notice it's flipped around because the products are on the left side of the math equation and the reactants are on the right side. So don't forget to do that. You got to flip the numbers around. So the CO2 is the one furthest on the left. It's the 393.5. You have 4 moles of that, so you multiply by 4. The H2O is the negative 285.8. You have 2 moles of that. Put that in brackets because you're going to have to do a multiplication within those brackets. Now you put a minus sign. Now another bracket. And now you go over to the reactant side on the left, and you have 2 times C2H2, so that's 2 times positive 226.6. And then you plus the oxygen. Oxygen is 5 moles, but it doesn't have any enthalpy of formation. It's 0. So just be sure you don't get your signs messed up here. That's the key. That's why you should write this out very neatly, carefully, and be sure you have your minus signs lined up properly. So you end up with the enthalpy of reaction there of negative 2,598.8 kilojoules. Of kilojoules, yes. Okay, there's a second example down below. So the calcium oxide and the carbon dioxide go on the left side of the math equation, and they give you the enthalpies of formation for them. There's only 1 mole of each. This is a balanced equation without any coefficients. It's already balanced. And then the calcium carbonate goes over on the right, and you subtract that number. And again, Be sure to keep your negative sign straight. Don't try to shortcut this. Write the brackets and the parentheses properly so that you don't mess up the negative signs. Okay, so that's the second example there. Now we're going to go into Hess's law. So we've done calorimetry, we've done enthalpies of formation. Now we go into Hess's law. This is the one where you use the enthalpies of known chemical equations to figure out the enthalpy of an unknown chemical equation. What it's really about is teaching you certain rules. It's almost like learning the rules of algebra in math class. You're learning the rules of chemical equations and how you can manipulate them. So Hess's law states that the enthalpy of a chemical reaction can be calculated from the enthalpies of individual parts of that reaction. Here's an example. So this is just our methane reaction right here. Okay. That's CH4 plus 2O2 gives you CO2 and 2H2O. We know that this reaction is exothermic and has negative enthalpy because if we hold our hand over a Bunsen burner in the lab, it's really hot. Notice that the water comes out as a gas, that's steam. So you have a different enthalpy than you would have had if that had been liquid water. Why? Because you have to give off more energy to turn water into a liquid, because liquid water has less energy in it. So you have to give out more energy to make it liquid. So in this case, it's water is gas, so the delta H is different than what you saw earlier in these notes. We know that the reaction is exothermic. Okay, now to convert the gaseous H2O to liquid water, we must remove more energy. So by removing energy, the water cools and the steam molecules condense and come together. The reaction for this is, so notice this is simply a change of state. It's turning the water as gas, as steam, into the water as a liquid. And to do that, you have to pull energy out of the steam, make the steam less energetic so the water molecules come together. And the amount that you need to do that is negative 88 kilojoules per mole. This means that 88 kilojoules of heat are released to the surroundings when water condenses from steam to liquid. Okay, so there you have the reaction of the methane reaction, the methane O2, CO2, H2O, turning the water into steam, and then if you want to turn it into liquid, you got to take out another 88 kilojoules, so that ends up being 890 kilojoules that come out to turn the water into a liquid. Okay, and this is just a diagram showing that. So the arrow, the longer arrow that's on the left, that shows the CH4 and 2O2 going all the way down to liquid water. It means it has to give off the full 890 kilojoules. Or you can do it in two parts. Turn it into gaseous water, into steam first, and then take the energy out of the steam. Okay? Let's move on. Okay, so now we're really getting into Hess's law here. Calculate the enthalpy change for the unknown reaction. So you have two carbon atoms, that's graphite in its most stable form, and three hydrogen gas molecules, that's in gaseous form, to produce 1 mole of C2H6, and that is a balanced equation, and that's also in gaseous form. Well, let's say we don't know that, but we do know the following enthalpies of formation. We know that to make carbon dioxide, we take carbon in its most stable form, that's graphite, plus O2 in its most stable form to get CO2 in its most stable form. And there's an enthalpy of reaction, we've already seen this number, of negative 393.5 kilojoules for carbon dioxide. Now, what about water? We have one H2 molecule plus a half of an O2 to give us 1 mole of H2O. Again, we have to have 1 mole in these enthalpies of formation. That's why you have to have the 1/2 in front of the O2 molecule. And then finally, we have 2 C2H6. Now, this one doesn't have just a single enthalpy of formation. It's actually a reaction. It's actually a combustion reaction. But you see the balanced reaction there, and that produces negative 3,119.6 kilojoules. Okay, so these are like little puzzles. So here's the best way to do these. Your goal is to get reaction number 1, is to create reaction number 1 by using 2, 3, and 4. And you're going to rearrange them, and you want everything that's not in reaction number 1 to cancel out, and then everything that is in reaction number 1 to show up in reactions 2, 3, and 4 when you add them together. the best way to approach these is find a compound in reaction number 1 that only appears once in reactions 2, 3, and 4. And so if you look at C2H6, it only appears in reaction number 4. You will notice that you'll notice that O2, for example, appears in all 3 reactions. So you don't want to use that one. And you also notice that water, H2O, appears in reactions 3 and 4. So you want to find one that only appears in one reaction, and that's the C2H6. So in your final reaction, which is number 1, you want to have 1 mole of C2H6 on the right-hand side of the arrow. If you look at equation number 4, you have 2 moles on the left-hand side. So what you have to do is turn equation number 4 around and multiply through by 1/2. So you want to get rid of that 2 in front of C2H4, and you want to turn it to the other side. So let's go over our rules for manipulating the reaction. You can multiply through any reaction by a factor, like by multiplying by 1/2 or by 2. You multiply the enthalpy by that same number. If you turn the reaction around, in case of number 4, put the 2C2H6 and the 7O2 on the right-hand side, and put the carbon dioxide and the water on the left-hand side. You just literally turn it around. Then you change the sign on the enthalpy. And then at the very end of the reaction, anything that's on the same side of the arrows gets added together, and anything that's on opposite sides gets subtracted or canceled out. Okay? So if we take equation number 4, and we turn it around, so the 2C2H6 is on the right-hand side, that changes our enthalpy of reaction down at the bottom from negative 3119 to positive 3119. So look down below where it says flip number 4 around and multiply by 1/2. So that's what you did. You flipped it around, that changed the sign to positive, and then you're going to multiply by 1/2 before you're done. Now what about the rest of them? How about C graphite? Well, you have 2C graphite in equation number 1. That's the equation we're shooting for to look like. And you only have 1 mole of C graphite in equation number 2. So what you want to do is multiply equation number 2 through by 2. So you have 2C graphite, 2O2, and 2CO2. And that means you're going to multiply negative 393.5 by 2. So look down below where it says multiply number 2 by 2. Okay, and then how about equation 3? Well, we need to have 3 H2s in our final equation, equation number 1. If you look at equation number 3, it's the only one that has H2 in it, and there's only 1 mole of H2, so you have to multiply that by 3. So you're going to end up with 3 H2 plus 3 halves. 3 times 1/2 is 3 halves O2 plus 3 H2O. And that'll do it. And so down below it says multiply number 3 by 3. So I've circled all the things that you have. Okay, that means you multiply the enthalpy there, the negative 285.8, by 3. Okay, so if you do all those math operations, so Hess's law seems kind of difficult. The enthalpy of formation method is much easier. It's the numbers just kind of work out simpler. You basically use all these numbers over here. And but that is Hess's law. But the important thing about Hess's law is understand the rules. But if you multiply the equation through by a factor, you multiply the enthalpy by that same number. If you flip the equation around, you change the sign. And when you add the equations at the end, you add compounds on the same side of the arrow, and you subtract compounds on opposite sides of the arrow. Okay, the last one is bond energies. So we've covered calorimetry, we've covered enthalpies of formation, and we've covered Hess's law. Now bond energies. Now this is only an estimate. And the reason is what you're doing is you're taking the known bond energies between two atoms and you're adding them all up. The thing is, it's an approximation, and the reason is this. If you have a methane molecule, which is CH4, it takes a certain amount of energy to break off the first hydrogen from that, to break that first hydrogen bond. So now that hydrogen is gone away. The second hydrogen is not going to take the same amount of energy. It's going to take probably more energy to break it off. And the third one more. So what you're really looking at in these bond energies are averages. So here's the way it works, though. It's tedious doing the arithmetic, but it's not hard to understand. So it's also called, by the way, bond dissociation energy, and it is the enthalpy required to break the bond of 1 mole of gaseous molecules. To use this method, you must write the Lewis structure for all the substances in the equation so that you know what bonds are being broken and formed. So here's an example. For the reaction 2C2H6, the one we just did, plus 7O2 gives you 4CO2 and 6H2O. So this one's kind of a pain in the neck because it's got so many moles of each of these. But if you see what we did below, you took the Lewis structure for each of those, the C2H6, and you have 2 moles of it, so you drew 2 of them. You have 7 oxygen molecules, you draw 7 of those. You have 4 of the carbon dioxide, 4 of those, and 6 of the water molecules. So what are you breaking? Let's start with the C2H6. You're going to break a carbon-carbon bond, and you have 2 different molecules there, so you have to break 2 carbon-carbon bonds. Then in each one you have to break a carbon-hydrogen bond. Count them. 1, 2, 3, 4, 5, 6. There's 6 carbon-hydrogen bonds in each of those molecules, but you have 2 molecules, so that's a total of 12. So if we go down below, look over in the left column, it says 2 times 6 for carbon-hydrogen, that's 12. So it's 2 times 6, and that's for the carbon-hydrogen, and that number is for a carbon-hydrogen bond is 414. Now, where do you get that? They would have to give that to you. So you do have a chart up on the Google Classroom that looks like this. It's the average bond energies. So if you look over at the 6th one down on the left side, it's carbon-hydrogen, CH, and it has a bond energy of 414. So you need 6 times 414. Now remember, to break a bond is energy going into the bond. That's a positive number. Anytime you have energy going in, like money into your bank account, that's a positive number. So the broken bonds, the ones on the left, which are the reactants, you're breaking those bonds apart to cause a chemical reaction, is going to be positive numbers. Now you have 2 carbon-carbon bonds, and that's 2 times 347. Again, you can look down at this sheet, and you see carbon-carbon single bond is right below carbon-hydrogen, is 347. So you have 2 of those. Okay, now with the oxygen, you have 7 double bonds between oxygens. That's 7 times, and you only have 1 for each molecule. That's 498.7. Again, you go down here, and you find oxygen-oxygen double bond is on the right-hand side down near the bottom. It's 498.7. Again, you're breaking a bond. That means energy is going in. That means the energy is positive. So that's 7 times 498. So you can see the equation being put together down at the bottom there. And now you're going to go to the product side. Products are when atoms come together to form chemical bonds of new compounds. They do that because they're more energetically stable. That's more favorable energetically. In other words, they're at a lower energy state. That means they're giving off energy on the product side when you put bonds together. So that means the energy is going to be negative. It's going out of the chemical reaction. So if we look at carbon dioxide, what you notice is you have 4 molecules. Each one has 2 carbon-oxygen bonds. So that's a total of 8 carbon-oxygen bonds. And if you see that down here, it's 4 times 2 times 799, so that's a total of 8 times 799, and that's going to be a negative number in the equation down below. 8 times, you got a minus sign and then the brackets. So everything inside those brackets is going to be a negative number. So 8 times 799, and finally water. Water, you have 6 water molecules. Each one has 2 oxygen-hydrogen single bonds. That's a total of 12 oxygen-hydrogen single bonds. So that's 12 times 460. And again, that's in those brackets. It's going to make it a negative number. And when you add all that up, you get negative 2759. So that's how much energy is released when you combust the C2H6 molecule. When you create a combustion, energy is given off. Okay, so many standard enthalpies of formation can be found in Table 5.3, 189, or on the Google Classroom, I should say here. And now I give you one last problem to do. And you can do that as you wish, but I've gone ahead and done it. If you understood what was above, then you're fine. Okay, again, I'm kind of at my standard time here of about 1 hour and 15 minutes. Please understand these, even if you listen to this a couple times. I know it's long. I'll put up some Google Classroom problems pretty soon. I'm kind of busy with other things. And but listen to this. Be sure you understand it. You've had all this before. And that's it. I'll talk to you on Monday with a new unit. Have a good day.